Alright, we begin a new section in Chapter 8 on linear programming. This is a topic that you will most definitely study in college if you're a business major or economics or finance or marketing, management, any of those kinds of business-related types of majors and degrees. And we do linear programming typically in college in a class that's called finite math. So that'll give you something to look forward to, you business people. Businesses typically have goals to maximize their profits, minimize their costs. And because there are certain things that affect this, whether it might be labor or cost of materials or increasing prices in energy, whatever it may be, what we call constraints, businesses have a number of constraints that may affect how they attain their goal. And so what we're going to do is we're going to try to look at these goals and constraints mathematically. And what we're going to start with is the idea of what's called an objective function. The objective function typically will be something that we're trying to maximize or something that we're trying to minimize. And notice here the notation I've written, z is equal to f of xy, indicating that x and y are your independent variables and z is your dependent variable. So this is going to be something that we're going to want to be able to interpret from a problem, be able to read the problem and come up with an objective function. We're also going to want to be able to determine the constraints, which turn out to be, as this chapter might imply, has to do with inequalities in two variables. So let's try an example, and this is the example that we're going to work all the way through this section. We're just going to do it in bits and pieces here. An office manager needs to staff the office. She hires full-time employees at $36 an hour and part-time employees at $24 an hour. We want to write an objective function that represents the total cost in dollars to staff the office with X full-time employees and Y part-time employees. This is very sloppy, sorry about that. Hopefully you can read this okay. And we're going to do this for 1 hour. Well, usually when I look at something that involves cost, like a cost function, I like to use the capital C to represent the cost function, but we're going to stick with their notation for right now. And I'm going to write this as z equals $36 for full-time, X full-time. That would be $36 times X for 1 hour for the full-time employees, $24 an hour for part-time employees. We have Y part-time employees, so 24 times Y would represent how much for 1 hour those Y part-time employees, and we're looking for a total cost, so we're going to add those together. And this would be our objective function. This is what we would try to, in this case, we're going to try to minimize because we want to minimize those costs. Now, from here, I'm going to go up to here, which is still using this idea right here, but now we're going to look at the constraints. This would be our objective function. Let me outline that. So, from this last example, suppose the office manager needs at least 20 employees. Notice the terminology here, at least 20 employees. It could be more, but no less than 20 employees, but not more than 24 full-time employees. So what we're looking at here is at least 20 total employees, that would be part-time and full-time, but no more than 24 full-time employees. Furthermore, and you gotta like a problem that uses the word furthermore in it, furthermore, to make the office run smoothly, the manager knows that the number of full-time employees must be greater than or equal to the number of part-time employees, so that they have those people that are in there working all the time to help out those that are only working part of the time. Write a system of inequalities that represents, there's that word, constraints, the limitations on what we're working with On the number of full-time employees, remember that's X, and the number of part-time employees, that's Y. Well, right off the bat, I've got to write down that X would have to be greater than or equal to 0, and Y would have to be greater than or equal to 0, because we're not going to have a negative number of employees. We might have 0, but we're not going to have a negative number of employees. It says here that the office manager needs at least 20 employees. So if this is the number of full-time, this is the number of part-time, added together, this has to be at least, which means it could be more than, at least greater than or equal to 20 employees. So I already have a system of 3 inequalities. But I think I can go a little further than this. It says we cannot have more than 24 full-time employees. So the full-time employees is X. X, remember, has to be greater than or equal to 0, but X would also have to be no more than, but not more than 24, so it could be less than or equal to 24. In fact, if I want to, I could take this guy here and just attach him right here and write it as an extended inequality. So now I have 4 constraints here that I have on this problem, but I think there is enough information for one more. It says here, to make the office run smoothly, the manager knows that the number of full-time employees, that's X, must be greater than or equal to the number of part-time employees, that's Y. So we have one more. X would have to be greater than or equal to Y. And what we have here are a system of inequalities in 2 variables. As you can see from the first 2, it's going to put us in the first quadrant, because X is greater than or equal to 0, Y is greater than or equal to 0. That means the ordered pairs have to have X values and Y values that are positive. That's in the first quadrant. And then we have some other restrictions here, or constraints. So from this, since we have this system of inequalities, it might make you think, especially since we just kind of looked at this in section 5, that maybe we need to graph this and look to see what kind of a region that we have that's shaded, that is an overlapping of all of these constraints. Well, when we graph the system of inequalities, this region of intersection is referred to as the feasible region. The feasible region means any ordered pair that's in that intersection will solve all of these. Now you say, well, there's infinitely many ordered pairs in a region like that. We can't plug them all in to figure out, going back to here to our objective function to figure out which one is going to minimize the cost. We don't have to. That's the good news. Okay, the vertices, or the corner points of the feasible region, are the only ordered pairs that we're interested in, because they're the key to finding the solution to minimize or maximize our objective function. We use what we sometimes call the corner point principle. The corner point principle says that if you're going to maximize or minimize the value of an objective function, it has to occur at the corner points. That one or more of the corner points is going to either give you the minimum value or the maximum value, depending on what you're looking for. So this is key, because we're all of a sudden breaking down a region that has infinitely many ordered pairs down to just the vertices, or the corner points, which is going to be a finite number. Now what we're going to have to do is we're going to have to go a little further with this example, and we're going to have to go ahead and graph this and see if we can find our minimized cost for this particular office manager that's hiring out for this company.